Hello, welcome to Freshman Orientation. My name is Dr. Edward T. Bednarz III, and I am an Associate Professor of Mechanical Engineering here at Wilkes University. So usually I hold these presentations in person, but given our circumstances this year, this one's going to be online. So I hope to convey all the information you would like to see and tell you a little about myself and uh, research work the students have opportunity to get involved in here at Wilkes, as well as primarily what is Wilkes University Engineering about. So hope you enjoy this presentation. Hope it's very informative. If you have any questions at all, please don't hesitate to reach out to me. My email address is listed here, edward.bednarz@wilkes.edu. So let's get right into it. Let's go back in time. So who am I? I thought it would be useful to kind of let you know who I am before you say, well, why should I listen to this guy? So I'm from Northeast PA. I'm from Hazleton originally, and I was a mechanical engineering student at Wilkes in kind of the transition of the new millennium. Graduated in 2001. So every year I make this, I'm like, wow, it's further and further back in time. But the good news is I've had most of the same professors that are still here. We at least have a few senior faculty that I had as when I was a student, Dr. Garishi, Dr. Razavi, Dr. Kaleem. And I can also still relate to current students since I've been in your shoes. And I'm from this program, and that's why I endorse it so highly because I think I went on and humbly say I had a successful career as an engineer before I transitioned into academia. So that's me back in the day, back in college. I had the goatee and the bowl cut look. That was kind of the fashion in the '90s, and I don't think I look that much different now. But I've aged 20 years since then. All right, so other activities at Wilkes. I played on the tennis team. It's always a common question. Can my son or daughter participate in sports while they're an engineering student? And the answer is yes. Yes, if you prioritize your time and balance um, your studies with extracurricular activities, absolutely. I was also involved in campus interfaith. I was involved in other clubs, ASME, American Society of Mechanical Engineers. So it's basically, college is an interesting period in someone's life because it's the transition into the real world. Parents are not here to tell you to do your homework, right? Professors, we do the best part we can to care. And, I do take attendance in my classes, but if you don't show up to class, I can't go knock on your dorm room and say, hey, why didn't you wake up this morning? So, it really is your transition to being an adult. And, when you're an adult, you have to show up to work on time. That's part of what's expected of you. So again, I think this is extremely relevant. What did I do with my Wilkes engineering degree? So in a nutshell, I got a full-time job working as an Army civilian, and I got to live out my dream of calling myself an inventor. So I'm going to talk a lot about what is engineering in general in this presentation. But it's a cool profession. I really do highly endorse it, and hope you get that after we're all said and done here. I went to graduate school while I was working. It's kind of another common question that I get, especially from my advisees that I meet with, every semester, and they're maybe contemplating grad school. They say, "Oh, well, should I just go right from my undergrad into grad school, or should I work first?" And it's kind of a complicated answer because it really is up to the person. But in my case, I was able to successfully start working, and then I had the Army pay for my graduate school degrees. So that's kind of one of the benefits to just to working first before you go to grad school. Of course, the drawback could be once you're out of school, you may not want to go back. So we do have opportunities here at Wilkes. Just to briefly plug what we have available here, that we have a master's degree in mechanical engineering, and if a student really does schedule their classes well, they can get both degrees in 5 years, 5.5 years, or 6 years at the very latest. So that might be something to contemplate, later on. So I did, I worked as an engineer for 12 years, but that did help me lead to my current teaching position, which is even more of a dream for me. I loved my job with the Army and I love being an engineer, but I love this 10 times more. I love working with students on a daily basis. I love teaching, conducting research, and continuing to learn myself, actually. So again, I graduated Wilkes mechanical engineering degree. Not to brag too much, but I had a pretty nice GPA. I studied hard. I worked hard. I was definitely blessed with gifts in math and such, but I did mainly work to get it. It wasn't just nothing was just handed to me. So all my students, I tell them as well. You have to work at it. I tell my children, you have to work hard in life. And nothing's just given to you. Anything worthwhile is a tremendous amount of sacrifice and work, but it's worthwhile. That's why it's worthwhile. So I graduated from UMBC, University of Maryland, Baltimore County, in 2006 with my master's degree, and then my PhD from the same school in 2012. So it took me several more years. It was kind of all but dissertation for a while. And it really took the motivation to say, hey, I really do want to finish this degree so that I could go on to teach. That was kind of, sometimes we need a little motivation. So I put up the logos for the two schools, but since this is the one that pays the bills for my family, we're going to highlight the flying W there. When I was at Aberdeen Test Center, the U.S. Army Aberdeen Test Center, ATC in Maryland, I had a lot of cool jobs I worked on. I don't want to list them all, but I just briefly show my primary mission was to design outriggers for vehicles in order to perform a lane change maneuver. So us as a testing organization, we were responsible for testing the performance of all types of Army vehicles. So smaller vehicles like Humvees, or the big, large vehicles that are the mine-resistant, ambush protective MRAP vehicles, and even higher than that, tractor trailers, whatnot. So they wanted to see how quick could it go through a lane change maneuver without rolling over. So you can tell that that's a pretty dangerous endeavor. That you don't want it to flip over. You don't want to ruin $1 million piece of equipment, and more importantly, you want to protect the driver. So I designed these outriggers, and if you can see my cursor, there's a foot pad that would skid off the ground, and this A-arm that would hold everything in place, and then there's a shock absorber that would dissipate the kinetic energy into the system. So, definitely you can see the engineering that would have to be involved in that to resist a vehicle traveling at a fairly high speed and making a quick turn from flipping over. This is another cool job I worked on. I designed modular platforms for ballistic testing. So basically, this was a big frame that we could put body armor in, and they could shoot at it and see how good the body armor is. So I got to witness some of the tests. I didn't actually get to fire the gun, but I was the design engineer. But the cool part of this job was I got to draw all this in SolidWorks. So this is all my drawings in SolidWorks, and then I got to physically build this. Sometimes as engineers, depending on where you work, you could be more hands-on than other places. Some places you're going to be literally in khakis and polo all day and just do your drawings and maybe check on the progress in the shop floor. Other places you may be expected to turn some wrenches and get hands-on. I'm going to talk a little bit more to that later on in my talk, but Aberdeen was cool that I got to do both. I got to do the design analysis, and I got to do some physical building and testing myself. And what you're seeing on the right is basically, it's called 80-20, and it's an adult erector set. That's the best way I like to describe it. It has all these different bolts and nut plates that you could slide in the slots from the extrusions, the aluminum extrusions, and you can basically configure something however you want. So, all I could do is just reach into my bin of piles of brackets and pull out the bolts, and it was kind of fun. You would have to know how to build it in the right order, because once you slid in a nut plate, you would have to slide in the proper one from the inside out. But yeah, it was pretty fun job to be working on. Then I worked for Aberdeen for 8.5 years, and then I moved back to the Poconos, and I worked for Toby Hanna for 3.5 years, also as a senior mechanical engineer. So I got 12 years total Army experience before I quit my government job and moved into academia. So while I was at Toby, I was a lead test engineer in the Environmental Stress and Screening Lab, which performed temperature and vibration testing. So we could have a shaker table to see how different piece of equipment, react it. It was mainly electronics equipment I worked on at Toby, and there was a temperature chamber that we could go extreme temperatures, cold and hot, as well as humidity extremes. Then probably the next job I worked on, possibly the coolest job I worked on, I'll show you in the next slide why I say this. I designed a 3-spar assembly for a 28-foot dish on a radio solar telescope network and installed on site in Hawaii. So this radio telescope network, there's several sites around the world, and it's basically just to kind of monitor solar flares. And it doesn't seem like a hard job. It's okay. Well, it's kind of a big dish, and I designed these posts that went up and held the focal ring in place. But here's the cool part: we got to go to Hawaii to install it. So this is Kena Point. It's on the northern edge of Oahu, and there's me back in the day, on top of a 35-foot man lift on top of a 1,500-foot cliff. And I was the one that actually had to do the installation because it was kind of my design. So that was cool to get really hands-on. And I'm like, don't drop the nut, don't drop the nut. So yes, I got paid to go to Hawaii. So that's kind of a cool thing with engineering. Sometimes you work for a company or organization and you get to do some neat travel. So that was awesome. That was a fun experience. So also while at Toby Hanna, I worked on something that led to my first patent. So I'm going to talk a little about my patents and intellectual property in general coming up. But here's my very first one. It's called the safety brace, and it was for a Q-37 firefinder, which protects soldiers from being killed when working on this pretty big antenna system, a 2,000-pound antenna. So you could picture this antenna as a dump truck bed that goes up and down, and it's driven by a lead screw here. So here's the motor, and there's the lead screw that would drive it up and down. And if someone needs to do maintenance under there, basically they're only relying on the brake of the motor to keep it from falling down. So this was a physical assembly that would go in place and lock it, and then if something catastrophic happened, it would put all the load into this safety brace and protect whoever was working on it. So there was a lot of reasons that I take pride in this assembly and this design. Again, safety seems to be a theme through my career that I really I take it seriously, that I want to make sure people are protected and they could do their jobs safely. So here's my patent number, basically 8.5 million something, and it was going too far ahead. And it was awarded in 2013. Okay, so how did we get there? How did I get to the patent side? And this is, where I could talk a little about engineering in general. So first thing before I design a safety brace is how much load does it have to take? That's kind of a very basic questions that engineers have to answer. So what you're seeing on the left here with all these pretty colors is CF Design. It's basically a computer program that would help analyze wind flow. So I modeled the safety brace at its typical angle, 77 degrees here. And I said, okay, here's the wind flowing by, and how much force from the wind is acting on the antenna. So this is kind of a common tool for engineers to use a computer to help assist our work. We need to know the math and how to do a lot of hand calculations, but it's also good to use computer to help out as well. So once I know the force from the wind and I know how much the antenna weighs, here's the force from gravity, and then here's the brace pushing back at an angle. This is all called the free body diagram. And this is actually something you learn as a sophomore. These arrows represent force vectors. And in statics, which is a class your sophomore year, how do we analyze a free body diagram to calculate unknown forces? So in this case, I had two known forces, the force from the wind and the force from gravity, and my unknown is, well, what's the force on the brace? So I was able to use, and then I was able to do this step using hand calculations actually. So I calculated from the free body diagram, assuming that this is in static equilibrium, which basically means that sum of the forces equals 0. So sum of the force in the x heft equals 0, sum of the forces in the y equals 0, and then here's the force from the brace. So then I used another computer program. It's called Finite Element Analysis, FEA. You may have heard that term. And that's going to help show the hot spots in the design. So anything that's green and blue is good to go. You can see here right at the gusset, we got this little red hot spot. So what that's showing is that's going to be your highest state of stress. And if you keep pushing, that's probably where it's going to break. You're probably going to crack that weld right there. So I did the analysis and found out that the safety factor was greater than 10, which is good. You know, it definitely should be safe under any extreme situation. You know, the antenna's up in the air and the wind's blowing violently, we should be good to go. But you know, many times and most of the time as an engineer, you don't want to trust just computer analysis or even hand calculations. You want to do physical testing. You want to see, okay, will it work? So you know, I was up at Toby Hanna at the time when I was working on this project, and I coordinated testing back at ATC, where I spent the majority of my career, and we got to put it in a big press and just kind of crush it and see how much it would break. And sure enough, it took a lot of weight before it could break. You know, I think we verified that it was a safety factor of 10 or greater. So that was a great test to do. It was kind of fun to take it to failure and break it, and then to demonstrate, yes, this will be safe. And so these braces are currently being manufactured for deployment in the field. So, and then one more thing I just want to highlight in this project before I move on to the next project. We had to build a plastic prototype before we got into full-scale manufacturing. So this was using additive manufacturing. And this is another emerging technology in the mechanical engineering field, where you know it's 3D printing, sometimes called, or vice versa. You could call it 3D printing additive manufacturing. Why is it called additive manufacturing? Small tangent. Traditional manufacturing is subtractive manufacturing. That's what mankind has been doing for thousands of years, right? You know, we take a piece of wood, we cut it, or we drill a hole in it, or right, or you could do it with steel or aluminum or what have you. Additive manufacturing, you're building something layer by layer, and in order to assemble your prototype. So this prototype, and I usually pass this around as a demo, you know, if this was an in-person orientation, but for now, just you could look at the picture. It's made of plastic, so it's nowhere near as strong as the real item, but it's there to test the form, fit, and function of the final design. So there is a pivot built in here, so this does open and close. So I wanted to make sure, does it fit around the lead screw like it should? And there's a little notch there to clear, you know, existing protrusion. So does it fit before I go ahead and create this large-scale manufacturing line? I just want to make sure everything fits how we think it should. So the rapid prototyping machine lays down plastic in 10,000 inch intervals in an iterative process, and it's basically using the CAD model from the computer in order to build it. So it's just a couple cool views showing what it looks like as it's being built. The white part is the plastic, that's what we're keeping, and the black is the filler, which is subsequently removed in a chemical bath. So you need the filler anytime you're going to try to lay plastic over air. You can't just lay the plastic, it would just droop down. So we have to build up these supports first. And then that's either chipped off or dissolved. Okay, so then that was the first patent. My second patent is the deflection plate leading into the force transducer. So the high strength deflection plate, which mounts underneath a mobile dynamometer to prevent a load cell from being overloaded. So this patent was issued in 2016. So this was kind of a fun project. This is actually my only patent where I'm the sole inventor. All my other patents, I'm co-inventors with other engineers, and in one instance I'll get to a little bit, non-engineer. But yeah, this was the only one that was a sole inventor. So it was a pretty fun project to work on. I needed to design this special taper in order to pull a tank without overloading the load cell. So I didn't want to break the load cell. So it's kind of like protecting the test equipment in a nutshell. This is the last major thing I worked on down at ATC. It's called the Bridge Crossing Simulator. So the Army tests these portable Army bridges, the green bridge there, and we can test it for fatigue life by either driving a tank over and over, or in this case, we wanted to create a machine that would do it quicker, safer, more cost efficiently. So this huge machine, the bridge crossing simulator, it pulls down with these hydraulic cylinders on these wiffle trees. And that's what actually applies the load. And it simulates a rolling load down the bridge. So we start pulling on this side and we start applying a couple cylinders and it sort of leapfrogs its way down the end. And then the whole bridge sags and deflects, and we call that one cycle, and then we keep doing that over and over and over. All right, so that was something cool I worked on, and related to that would be my patent for force transducer relating to my BCS work. So that was, and that was actually my dissertation for my PhD too. It was just ways to identify loads on a beam or bridge using strain gauges. So that's, I don't want to get too much into that at the moment. Okay, my next two patents, I'm proud to share this one. It's my co-inventor, my partner, and my wife, Heather. So Heather is a occupational therapist, and she had an idea for these two inventions, based on her experience in her job. The first one was for an adjustable wheelchair, so that it would basically grow with the patient. Wheelchairs are in discrete sizes, but she wanted to make one that would actually, you could use a crank handle and adjust the screw, and it would get bigger or smaller. So it would adjust perfectly to the patient. So there's a lot of great applications for that. That either a facility like a nursing home, they don't have to stock as many wheelchairs, right? They could, instead of having an 18-inch, a 20-inch, a 22-inch, just for all these different patients they may get, they can just stock a couple of ours, and they'd be able to adjust it. Or if a patient got sent home with from Medicare, they got sent home with a wheelchair, and then they needed a different size one as they got older, then they could adjust it themselves. The second patent I'm equally proud of was a pressure redistribution system. So if someone is partially paralyzed and they're sitting in one spot for too long, they can develop pressure ulcers, which is a very nasty thing. So we developed a system that could actively see if they were sitting in one place too long, and then it would sense it and alert the caregiver to reposition the person. Or if no one was coming along to adjust them, it would actively inflate an air bladder and then move them themselves. So these are great collaborations. Again, I do emphasize that we are all co-inventors and all equal partners in this. That Heather, myself, and two different groups of students. These are both two different senior projects, separated by a couple of years. So we paid for the patents ourselves through the patent lawyer, and now we're actively trying to sell both patents. So we'd like to sell it to a company that could actually go ahead and make these and get them into production and help people. So we're definitely very proud of that. And myself and me and Heather, we have several children together, so we're co-inventors in life too, besides just in engineering. Okay, so basically after spending all that time at Aberdeen Test Center and then Tobyhanna Army Depot, I returned home, and I really do emphasize home, coming back to Wilkes University, because I think I always knew I wanted to be a professor. Even when I was a student, I was a TA, teacher's assistant, and I liked helping my fellow classmates learn the material. So I would get up on the board and I would kind of do example problems for everybody, in my class or the class below me. So I think I always, and then even when I was working at Aberdeen, before I left, I set up a tutelage session of, okay, this is everything I know about outriggers, guys, and this is everything I know about the bridge crossing simulator. And I think even my coworkers were like, wow, you should be a teacher. So I started as an adjunct professor back in 2010, which is 10 years ago. Wow, can't believe it's been that long. While finishing my dissertation. So, as I mentioned, that 2012 is when I got my PhD. So I started just teaching part-time while working at Toby. And it was really after I got my PhD, then I actively pursued trying to get a job full-time here at Wilkes. So I'm going to pause the video and pick it back up. Okay, so my next part of my talk is why become a mechanical engineer? Or why even become an engineer in general? Here at Wilkes, we offer several disciplines of engineering. We currently have mechanical engineering, electrical engineering, environmental engineering. We are pursuing creating new programs in civil engineering and material science engineering, but I could speak mostly to mechanical engineering because that is my career in the department I teach in. But I'd be equally as happy as if you choose one of these other engineering programs we have at Wilkes. I think they're all great programs. Think of what an average person would consider a high-paying profession. Yes, the average person down the street, and they're like, "Oh yeah, medical doctor, lawyer, some along the lines." But maybe people don't realize that the engineers get paid really well, actually. The 2014 median salary for mechanical engineers nationwide is $83,000. So that's not too shabby. Starting off, students can expect maybe 60,000 around that, maybe lower, maybe higher. And then by your mid-career or even as a senior engineer, you could be making 80, 90, and you can even be making six figures, truly. So there's great earning potential. I know, not to get off another little tangent, but it's kind of what I do. I know there's a lot of debate now as to whether college is worthwhile, right? Like, well, if you went just to be a roofer right out of high school, you can make money right off the bat. Where in college, you have to take out a loan first. That's true, but look at the earning potential working as an engineer versus working in a manual labor position, and you easily would pay that college loan off in maybe 5 years, 10 years, and then from then on, you're making even more money, and you're not breaking your back truly. So something to consider. How about the job potential? What it pays is one thing, but hey, will my son or daughter have a job when they get out of school? And these are actual salaries from American side. These are actual statistics from the American Society of Mechanical Engineers. In 2014, there were 277,500 jobs nationwide, and it's predicted to grow by 200 to 290,000 jobs by 2024. So not only is mechanical engineering fun, but it pays well. So and there's a good potential. It's the number one engineering profession in the country, mechanical engineering, and even in this area, there's a lot of great companies. I'm going to talk to them a little bit about our co-ops and internships and all that. But just trust me for now. Okay, so this is the finance and the jobs prospect, but I think here's the real reason you'd want to go into engineering. Why do you want to be an engineer? At a physics conference, are things made of stuff? At a philosophy conference, is stuff stuff? At an engineering conference, awesome stuff. Could it be more awesome? Giant laser, ultra space jets. And truly, to me, I'm 40 years old, but I'm still kind of a kid at heart. I love watching the SpaceX go up to the International Space Station and seeing all the different emerging technologies with, 3D printing and robotics and artificial intelligence and all that cool stuff. So definitely a fun profession. So you do have to work hard to get there, though. It's like, okay, sign me up today. I just want to be an engineer. So here I'm going to talk a little about the mechanical engineering curriculum, and here's how we have it structured at Wilkes. So it's structured for a 4-year program. So basically, your first couple semesters, 2, 3 semesters, you're taking a lot of similar classes to all the other engineering majors. So mechanical, electrical, environmental. They're all taking the calculus foundation courses, the physics foundation courses, your intro to statics, intro to electrical circuits devices. So for the most part, you could go 3 semesters without really having to pick a discipline. But I would say by fourth semester, that's when it really does break off. So pretty much everything you see in the fourth semester is unique to mechanical engineering. Um, Actually, environmentals, they also take strength of materials, but every other course, mechatronics, dynamics, thermodynamics, machining, those are all just unique to mechanical engineering. So I would say hopefully by end of your sophomore year, this would be spring sophomore year, you would have a handle as to which discipline you would like. So then when you get to fifth, sixth semester, we're starting to get into more upper level core classes. These are all still required. Mechanical engineering has several sub disciplines. So when you're working in the real world, you may be in the fluids, heat transfer, thermodynamics system, or you may be working in robotics and controls. Or my personal background is solid mechanics and design, engineering design. So, there's a lot of different niches. At Wilkes, we have the philosophy that we want to offer our students breadth and depth. So we want to give them breadth, and they'll get exposure to all these different disciplines: machine design, fluid mechanics, vibrations, heat transfer, and so forth and so on. But we also want to allow the students to get depth within a particular topic. So I can talk to the tech electives I teach. You'll see here by the time you get to seventh, eighth semester, there are tech electives. There's a science elective, a couple tech electives, free elective. Um, so I teach advanced CAD, and I teach advanced machine design and inverse problems in mechanics. So these are all, if students say, oh, wow, I really like machine design, I want to learn more in depth. I want to learn about cams and gears and additive manufacturing and 3D printing. Or say someone takes material science course and they say, I want to learn more about nanotechnology or polymers. These are other tech electives they would have to choose from. So that's kind of how it's structured. So you see that a lot of the core classes are completed before senior year, and then your senior year is mainly left up to a couple core classes, but mainly the elective classes as well as senior projects. That's another major course that I'm going to talk about. Senior Projects 1 is your fall semester. That's kind of working in a group and designing a product. And then Senior Projects 2 is your spring semester, where you're completing your design, building and testing your prototype. And all along, you're working with a dedicated project advisor to help guide you along the way. So senior projects is definitely one of my favorite things to be involved in. I've actually been the coordinator for the senior projects course the last few years, and it's been a blast. I love working with senior projects. I just love the innovative aspect of engineering and creating something new and helping these students come up with something on their own. There's also general education classes, and I'll talk about that in a second. So here's the overall flow chart, and I guess when I do this live, it's hard to explain everything. But if you're watching this on a video, you could just pause this and study a little more. And we can also get you physical copies of this if you request. But you can kind of see the flow chart. There's a sequence. Math 111 is Calculus 1. Math 112 is Calculus 2. Math 211 is differential equations. So you can kind of see you need to pass Calc 1 before you get into Calc 2. You need to pass Calc 2 before you need to get into DiffEq. Same goes for your Physics 1 class, your Physics 2 class. I could talk just briefly to our mechanical engineering curriculum that we have. You need statics, which is the free body diagrams I was talking about previously, in order to learn about strength of materials, which is now you have a structure that's under a certain force. How do we calculate the stress, strain, deflection? And then which leads into machine design is, okay, well, now how do we design a system to interact with each other? And how do we procure which different types of materials are the best? And how do we consider cost versus quality versus time to build it? So you could kind of see the progression that these are all prerequisites to the next one in this series. The solid lines are prerequisites, which mean you absolutely have to pass Calculus 1 to get into Calculus 2. The dashed lines are co-requisites, which means that it's recommended that you take Calculus 2 before Physics 2, but if you absolutely need to take Calculus 2 the same semester as Physics 2, that's fine. And that actually helps students stay on track. Perhaps if they haven't come in with, they're not able to take Calculus 1 the first semester, and they need to start out with pre-calculus, they could still kind of keep going without losing any time and still graduate in 4 years. So kind of that's my little segue into where would you start with your math. So the math department has set the following criteria for a math placement test. And this will see if a student is ready for Calculus 1 their first semester. And that's the typical start in the flowchart I just talked about. Or if the placement is between 18 and 29 on the test, the student could start with pre-calculus, which is Math 100. And then he or she can take Math 111 semester 2, Math 112 either during that next summer or semester 3 and so forth, but they should still be able to graduate in 4 years, no problem. The more challenging one is if a student gets score below 18, and that's Math 94, which is college algebra. So that is a lot more challenging because a student won't be allowed, going back quickly here, the student won't qualify for chemistry that first semester, so then they would have to take it later on, and then that may push back when they could take physics and so forth. So it's highly recommended that if you didn't at least get into Math 100, you find a way to reschedule the placement test. As of the recording of this video, I'm not entirely sure how to do that remotely, but if you reach out to me, I'm sure I could find you the right information. Typically, it's during orientation weekend that students could reschedule to take it in Stark Learning Center, but most likely you'll be able to just do it online, retake it again, or you can reach out to someone directly in the math department. I'm going to talk about Math 94 in the next slide, so I'm going to just pause that thought for now. Let's go the other extreme. What if a student has passed the AP Calculus exam in high school and is offered the credits for it? Now they can elect to take Math 112, which is Calculus 2, right off the bat in semester 1. So the benefit of that is it opens up credits for a minor later on. And so that's good. It's really a decision a student has to make. I get advisees who say, well, yeah, I could take these AP Calculus credits, or should I just retake Calculus 1 in college to make sure I really understand it, probably get a 4.0, and I can't make that decision for you. But and we could talk more in our one-on-one meeting, but it really is the decision the student has to make. If you felt comfortable with Calculus 1, you said, yeah, I really understood it in high school, and I got a 4 or 5 on my AP exam, and I'm ready for Calc 2, great, go ahead and do that. Because again, that opens up credits later on. Or if you say, no, I really would rather make sure I learned it so that I'm really good for Calc 2 my second semester, that's fine too. I'd be happy with either decision, whatever the student is comfortable with. Okay, so it's always a challenge to help advise students to still graduate in 4 years if they start out with Math 94. And my department, we really took this challenge to heart because we want to help our students succeed, and we don't want to say, oh, sorry, you guys stick around another semester, or worse yet, another year, right? So we sat down and we looked at the flow chart, and here's the typical flow chart, and we said, okay, well, where can we help the student if they can't take Math 111 right off the bat, they have to take Math 94 here, Math 100 there, how can we help them catch up? And this is the best plan we came up with, and actually it is doable in 4 years, truly. Now, there's going to be some summer classes involved, But that's mainly due to the fact that instead of taking Math 111, you you have to take two extra math classes. You have to start with college algebra and then pre-calculus. So it's really not that much of a stretch that you'd have to take some summer classes along the way. So here's the plan. And again, you could work directly with your advisor to finalize this plan, but this is in general what we would recommend. You'd be still taking CAD, English composition, and first year foundations, which is what the other freshmen would be taking. But missing from this list would be the chemistry. So instead of that, you'd be taking a general education class. Then in your second semester, you could qualify for chemistry for engineers and the lab. Um, but then you wouldn't really qualify for any of the other typical classes on the flow chart, so you'd have to take 3 Gen Ed classes. So the good news is you'll get a lot of the Gen Eds out of the way. Then that summer, that's when you would really have to catch up. Take calculus, physics, and physics lab, which would be eight credits total. But then by the third semester, you're more or less back on track. Then you're back to Calc 2, and here's your physics classes. So anything in italics means it's deviates from the previous recommended sequence. So you could see how the third semester really lines up well. The only thing in italics is Calc 2. Fourth semester, you're mainly caught up, but you're taking 2 classes that the normal flowchart would have recommended for the second semester, which was scientific programming and material science. And then that second summer, you would take differential equations. And then that's pretty much it for summer classes. So really only 12 credits total in the summer. And then by the time you get to junior and senior year, you can see there's really not too many classes out of sequence. You know, multivariable calculus, which was a recommended fourth semester class, now it's taken fifth semester. Mechatronics, which was a sophomore class, now it's taken junior year. But other than that, everything else is back on track, and the students should be able to graduate on time. And then here's what the extended flowchart would look like, starting out with the college algebra track. So that's showcasing. Here's the extra summer courses along the way. Now I mentioned general education courses. To elaborate a little more what that is, it's and you know, pretty much every school does this, but here at Wilkes we have separated into 4 areas that every single student at Wilkes needs to know when they graduate, or at least have exposure to each area, to make them well-rounded students, you know, liberal arts education school. Area 1 is the humanities, so they would need 9 credits in English, history, philosophy, or foreign language. So basically 3 classes out of this area. Scientific world, this area 2 is met by just engineering courses, so students wouldn't have to worry about area 2. Area 3 is 6 credits, which is 2 classes, and I recommend that students take economics 102, and then they could choose one other class, either anthropology, political science, psychology, or sociology. And then the last area is visual and performing arts, so they would need 1 class, either art, dance, music, or theater. So it's really not that many Gen Ed classes if you think about it. 3 plus 2 plus 1, so that's 6 Gen Ed classes. In the typical flowchart, I'll just go back one last time here. You can kind of see how it's recommended to be spread out, maybe 1 a semester for the most part. Okay, so that should wrap up the Gen Ed. And then continuing talk about curriculum, we have the first year foundation class. Sorry to keep jumping back and forth, but here's your FYF 101. This is actually the only class that every incoming freshman needs to take at Wilkes. It's a class that's supposed to transition students from high school into college. So it has a lot of core principles that students need to understand. Oral skills, writing skills, diversity, critical thinking, and so forth. But how it's delivered is up to the instructor. So, there's classes on going global, and specifically, I teach a class. It's called engineering design. So that's why I bring it up in this talk. They strongly recommended for engineering majors. And here's the course description. Engineers are inventors who create something new and change the world. In this course, you will learn about the exciting and challenging career. The course will cover the evolution of engineering as a profession, as well as where it is going in the future, robotics, 3D printing, etc. There's hands-on projects for the students, such as building an earthquake-proof tower, having egg drop competition, and innovation is within your reach. So as of right now, there's only one section offered, unfortunately, but we do hope to expand that in the future. So if you have a chance to get into this class, great. You'll see me in the fall. If not, there's lots of other great classes to pick from. Just take a nice read at each course description and try to pick which one's most applicable to you and which one interests you the most. Sections do fill up, so you may not be guaranteed your first choice, but I know the FYF committee has done a great job at least trying to get students paired with one of their top 3 choices. I think over 90% of students get at least one of their top 3 choices. The only class that you can't opt in or out of is FYF 101Z, which is called Intelligence Applied. And this students would be assigned to this class and may not elect in or out of it. All right, so I'm going to pause the video here. Okay, so the next thing I want to look at is kind of a common, frequently asked question. Every time I end one of my orientation talks, and especially to the parents, I say, hey, does everyone have any questions? I guarantee one or more people will say, is there any kind of computer my son or daughter needs to bring their first semester at Weld? So great question, and we as a department actually did put together a recommendation because it is such a commonly asked question. So you can pause this screen if you need to and study it a little more, but basically if you want a specific graphics card, a recommendation is here, hard drive recommendation is here, and basically this is sort of the general statement that a list below of software that students use over the 4 years is kind of listed on the next page. The software may be installed as needed. Free or reduced cost student versions do exist, and students will be able to download them. Students may wish to review the list with the store from which they are purchasing a computer to check that the machine being bought will handle the software adequately. But please keep in mind that computer labs do exist on campus that have required software installed. So students can use any computer lab. So they do not need, in theory, a computer, but it really is highly recommended, especially after living through the COVID-19 semester for spring of 2020, where our students, and actually nationwide, global wide, so it's not just us, but basically students were sent home midway through a semester and then asked to continue with online instruction. So I think that those that had computers that they were used to working on were probably way more of an advantage to just continue their work. So yeah, it probably is an advantage to get your own computer instead of just solely relying on Wilk's resources. That being said, if you don't want to try to download one of the specific CAD programs like SolidWorks or AutoCAD, or you think that the computer you have can't handle one of those programs, you're probably okay. For a normal semester, there are computer labs available with those specific software programs loaded. So I would say 99% chance you'll be okay. But it is good to have a computer that you could work on lab reports and presentations and stuff like that from home or from your dorm room. So freshman, sophomore year, you'd be using the Microsoft Excel or Microsoft Office Suite, Word, Excel, PowerPoint, and they come loaded on a lot of standard machines. AutoCAD student version, like I mentioned, SolidWorks student version, recommend it, but definitely not required. Same with MATLAB or some sort of C compiler. By junior, senior year, students are starting to get into ANSYS or maybe even Wolfram Mathematica. And then just the final statement about that, students are not provided with the computer, but students are given access to the software for the classes they're able to install on their own computer. And as I mentioned, computer labs are available 24/7. The College of Science and Engineering maintains a computer room in our main academic building, the Stark Learning Center, that students may access 24/7 with computers providing specialized engineering software. And if you need to pause either one of these screens to look at it in more detail, feel free. Okay, so next thing I want to look at my teaching philosophy. You know, Dr. Ed Bednarz teaching philosophy, but I think a lot of my colleagues have similar teaching philosophies. So it is, no matter who you get at Wilkes, you're going to experience similar level of passion and care. You know, that's kind of one thing I want to emphasize right off the bat. So first thing I do is I go over the theory, either on a projector or illustrate on the board. I like to give my students my own cliff notes ahead of time. You know, here's the typed up formula. Here's how you calculate bending stress on a beam. And then I say, okay, well, this is what the different variables mean. But then I go over problems real time with the class, encourage them to bring their calculator class. I encourage them to participate. You know, I have a system where I try to encourage the most diverse class participation as possible. You know, that not just the same one or two students are answering it. I throw I have this bag of wheat pennies, you know, from the 40s and 50s, and if someone answers a question or asks a question or participates, I throw them a penny, and at the end of the class, I take attendance every single class. But if they had a penny, they throw me the penny back, and they kind of get a little plus mark. And then, you know, when I'm tabulating grades at the end of the semester, I'm like, oh, wow, Susie or Joe, they really they participate a lot. You know, I see 15 plus marks for them throughout the course of the semester, and they only missed one class or no classes at all. So, you know, that level of dedication, commitment may actually bump them up a half grade. You know, if they were on the verge of a 3.5 or 4, I may bump them up to a 4.0. So, you know, I'm looking for them to be actively involved, participate. Every class I teach, I draw on my experience as an engineer. So I previously went over the 12 years I was working as an engineer, and I still consider myself an engineer. You know, I graduated 19 years ago, and I still consider myself an engineer because I'm still involved in projects and working with students on engineering. So, you know, I draw on all my experience as an engineer. I like to incorporate group design and research projects. It encourages creativity and collaboration. You know, a lot of times, most of the time, I would say in the real world, and even as parents, you could attest to this, that you're going to be working on teams, and there may be people that you may not get along with, but you have to put any personal differences aside and get the job done. So, you know, there's been a lot of times where I've had a team and students haven't got along for one reason or another, or, you know, typically it's someone's not doing work and the other ones are carrying their load. So I try to meet with them as early as possible, as soon as it's brought to my attention that hey, this, you know, so and so isn't doing what they said they were going to do, and I try to kind of hold a group counseling session and say, okay, everyone needs to pull their weight, and you got to work hard. So you know, I try my best to help them. I also encourage computer modeling, analysis, and all current tools we have as engineers. What's my engineering philosophy? So this is another great topic. I like to incorporate in as many classes as possible. Um, Especially, it's fun to have class discussions and say, okay, you're enrolled to be an engineering student, and you want to be an engineer when you graduate. What is engineering to you, right? You know, it's always a fun topic, especially if someone's not entirely sure what it is. But you know, okay, well, let's talk about it more. Here's my favorite definition of it, and forgive me for not knowing who this quote came from, where a quote came from. I don't think I developed it on my own, but I love it, so I use it all the time. Engineering is the practical application of science for the benefit of mankind. So scientists, they like to discover for the sake of discovery, and that's great. The physicists are always trying to find out, how do galaxies form, and I watch shows on the universe all the time, so I love it. And Brian Greene's my favorite physicist, and he wrote books on um, string theory and parallel universes, and and that's all fun stuff. But engineers, at the end of the day, we want to know, how do you use that science to make people's lives better? How do we increase transportation and energy efficiency and entertainment and just overall quality of life? This is what engineering is. That's what it is at its core. So I think you, as a student, likely entered engineering through one of two paths, or maybe you kind of entered through both. I think most students either came in as the practical side, quote gearhead, or the theoretical side, the book smart. And if you're wondering where I came in, I was the latter. I was really good at calculus in high school and physics, and I wanted to be a math major actually, but it was my calculus teacher in high school said you should take physics your senior year, and if you like it, go into engineering. And that's literally all she said. And it was a wise career advice to me because I love engineering, and you hear how passionate I am about it. So, but since then, you saw all the hands-on things I got to do as an engineer, and so I feel pretty confident about turning wrenches, drilling holes, kind of try to do a lot of fixing stuff around my own house that I can. Um, my wife always laughs anytime I get an opportunity to use a power tool. I love it. But I think at the end of the day, your goal should be to bridge the gap between these two. A truly successful engineer can perform theoretical analysis and also be hands-on in order to get the task accomplished. So depending on your actual place of work, you may be asked to lean more towards one or the other, but you're most marketable when you have a balance. I equally put on my resume that I have skills in different software and analysis, but machine shop skills. I put that on my resume. So, I think it makes you more marketable, more balanced, and more valuable as an engineer if you actually understand how things go together. So, my goal is to inspire you to invent, create, and excel in your life after Wilkes. I love success stories of former students that go on to do great things in the engineering profession. And I have a couple of wonderful ones to show you towards the end of my talk today. What makes engineering different? And here's myself with my adjustable wheelchair team that I'm co patent holders and partners with Heather. And what I'm going to show next may seem cliche, but it's absolutely true. Faculty that cares. Wilkes is primarily a teaching school where undergraduate education is emphasized. So we do research, and we encourage students to be involved in research, but my primary job is showing up day to day and teaching my class and making sure the students understand machine design, and they understand fluid mechanics, and they understand um, all the different courses I talked about. And I could truly back up this statement with my whole heart. Our students are well prepared for industry and graduate school. And I'm not trying to be a used car salesman when I say that. And I know it for a fact because I worked with engineers from the big names, the Drexels and Penn State and Lehigh when I was down in Aberdeen and Toby. And I always thought to myself, boy, I know just as much, if not more, in certain areas than you do, at those big name schools. So I really think that Wilkes offers a lot of bang for the buck. And, our students, they go on for successful careers. They go, we have a professor, he went to Stanford for his PhD, and now he's back teaching physics. And I know many students that are in grad school currently going for their master's, PhD, working for in industry all around the area and the country. So the instructors offer this hands-on experience. Kind of going back to what I said previously, that a good engineer needs to know both the theory and the hands-on aspect, and our whole curriculum is structured that way, that you're taking the heat transfer lecture, and here's the theory behind conduction, convection, radiation, and then you go and do the hands-on lab, and you're actually going to do experiments to see, oh, well, how does the heat transfer, and how do I measure it at different places, and how do I comprehend this, analyze it, write a report where someone else could read it and understand it. This is what engineers do. Last point on faculty that cares, I know the names of my students. My office is open. They can reach out to me. I'll help them as best I can. I have students email me all the time about what would you recommend on this job choice I have, or I'm having problem at work on this. How would you handle this situation? Or here's a technical question for you. Is this a beam and bending or torsion? I truly do pride myself that my students aren't just a number or another face in the crowd. And part of it is that I do take attendance every single class. So, maybe I'll have a class of 25 students and I'll know all their names by week 6, week 7, and I can see them in the hall and, oh, hi Bob, hi Joe, hi Ahmed, and they'll know who I am, and they'll say hi to me back. So we definitely are faculty that cares. And here's a great picture getting dirty at orientation. Every year they have community service. So I think this year we were planting trees, and then the students started having fun then. Like, they didn't really get that dirty. It wasn't like they were in a coal mine, but they started just smearing dirt on their faces and stuff. But it was a nice community service for, I believe it was like a local nursing home, and we were planting some bushes for them or what have you. And there's me on the left with my son Eddie, and you could tell that this was long ago because now Eddie's about my height. He's 14 now. He's probably 8 in that picture, I would imagine, 9, because all those students have then gone on to graduate 2 years ago now. Oh, I'm getting old. Okay, so I'll pause the video here. All right, so to highlight a few more things we're proud of here at Wilkes, we were awarded a $3 million grant from Pennsylvania in order to improve on the following labs that are cutting-edge technology: additive manufacturing, the 3D printing lab, nanotechnology, and bioengineering. So here I have just a short news clip showcasing.
Learning in a 21st century environment, a local university has a new state-of-the-art engineering department for students. Eyewitness News reporter Cody Butler takes us inside.
A crowd of more than 100 people came out to Wilkes University Friday to dedicate the new Mark Engineering Center inside the Stark Learning Center.
I went away for the summer and I came back and I was just totally impressed with how modern, this new wing of Stark looks.
Associate Professor of Mechanical Engineering Ed Bednarz says the newly renovated section has 3 new facilities, which include a bioengineering, nanotechnology, and 3D printing with new labs, creating a true state-of-the-art facility for current and future students.
Our goal is to get our students relevant jobs in their field when they graduate, so we want them to have their hands right in current technologies.
It's an $8 million investment in STEM education with a 23,000 square foot overhaul renovation. Randy and Robin Mark gave a leadership gift supporting the project. Randy has served on the university's board of trustees since 2013.
We have the opportunity to help inspire innovation and hopefully encourage success among the students.
Wilkes University's president, Patrick Leahy, says the country has seen a gap in engineering graduates, which he says has hurt the industry as a whole.
We as a nation need to educate more engineers in order to remain competitive worldwide.
The new renovations are a step in the right direction here in Luzerne County. In Wilkes-Barre, Cody Butler, Eyewitness News.
That project took 16 months to finish, and it was finalized in August. The construction was completed in many phases to avoid disrupting classes during the school year.
Okay, so definitely very proud of those new facilities we have. Okay, and next one I want to brag a little about Wilkes as a university. Here's from a journal, Economist, and it was their first ever college rankings. So basically, they took a look at students with their expected earnings versus median earnings after graduation and said, well, how well did the individual university improve their likelihood to succeed in life? And this is phenomenal that Wilkes was ranked 25 out of 1,200 colleges nationwide. And look who we beat out at number 26, MIT. You might have heard of them. So, this is the whole university in general, but I would suspect that most of this is coming from engineering. Not being egotistic, towards my program or my departments in general, but I think really students are graduating, getting jobs in this area, $50,000, $60,000, and if anyone's from this area, that's a lot of money, for this area. It's definitely a lower cost of living, Northeast Pennsylvania. So in order, to be making that, especially right out of school, that's great, and makes it a lot easier to pay off the loan and to have a more comfortable living later on. So I did mention that we offer hands-on labs, and it does come from our smaller class size. We typically, for lectures, like to stick between 20 and 30 students for a lecture. It's just a big enough class that, again, I could learn everyone's name, call on them if need be. It's just a more easier environment to learn. For the labs, we try to stay even smaller than that, perhaps 8 to 12 students per lab. And that really allows the students to get hands-on with the mechanical design lab, the vibrations lab, the fluid mechanics lab. Here I'm showcasing the wind tunnel on the fluids lab. And I remember even as a student thinking, wow, this is the coolest thing in the world. I'm not just watching a TA from 20 feet away do the experiments. I get to actually push the buttons on the controllers, take my own data, and get experience on all these different pieces of equipment. So great experience for our students. And again, this is probably one of the hallmarks of our program, why I do say students are so prepared for the real world, that they not only get the experienced lecturers helping them learn the theory, but they actually get the experienced lecturers, and experimentalists helping them understand how these equations are applied in the real world. Students are given an opportunity to conduct research along with the faculty members. And for most schools, that's PhD level, master's level maybe. But here, we do have a master's program, as I mentioned previously, but also undergraduate students. We do encourage undergraduate students to get involved in faculty and conduct research. Typically they could do it for an independent study course and get course credit. I've had a couple publications with students, at the undergraduate level even, and conference presentations and so forth. So I think we are unique in that aspect. And I don't think many schools do that. That research with faculty can be conducted at the undergraduate level. Below, what you're seeing is a force transducer on a simulated Army bridge, kind of tying it back into my intro on my own research area and interests. That's simulating that big, large bridge crossing simulator that I showed from Aberdeen Test Center. Here's kind of a small scale. We had a tank that we drove over, and we're trying to measure the dynamic forces from the strain gauge electrical measurements. And there's just kind of a view of my lab during the end of senior projects. So you could see students working on a variety of senior projects and class projects for my advanced machine design lab. And then you kind of see the kids' toy on the bottom right. That's for an outreach event. So this was just kind of a fun picture I wanted to capture, that like the chaos, but also the collaboration going on. Another hallmark, I think, of our school is we offer a cooperative learning experience with local companies. So Northeast PA, if you're not familiar with this area, it's we don't have a huge company like Ford or, that's employing thousands of engineers, but there's a lot of local companies and they all hire, several engineers or several dozen engineers, and we have great partnerships with them where they specifically seek out, oh, I need a Wilkes engineering student to fill this position. So we have great partnership here. And this offers students the opportunity to get hands-on real-world experience while they're still in school. And they could get it for course credit or not if they opt not to. So, but actually, regardless if they take it for credit or without credit, the majority of the internships are paid. So that's great. I know other majors, they may offer unpaid internships, just, oh, you're getting experience. But no, students are getting paid maybe $15 an hour, to work or more, to work as an engineer. Here's just some of the companies in our local area that we partner with and all the students have been working with. I do recommend to all my students, actually, that they get some sort of experience while they're in school, either over the summer if they don't really want to interfere too much with their schoolwork during the semesters, definitely over the summer, or, during the school year, they can work 10 hours a week, 15-hour a week at a company, something to put on their resume to differentiate them from other competitors when they graduate to try to get them a job. Because that is our number one goal. We want to prepare the next generation of engineers to, get a job and be productive in the real world. I do want to highlight Sharon Castano. She's shown on the right with local radio celebrity Amanda from KRZ on the left. And Sharon's phenomenal. She's the director of internships and co-ops at Wilkes. And she works with all the different departments, but I think she especially likes to work with engineering students, and she really cares about our students and tries to help them with their resume, interview skills, applying for jobs, and what have you. Here's a great picture showing a collaboration with a local company. You can see myself in the Steelers jacket, along with 3 of my students. And so we partnered with Mountain Productions. They're a local company in Wilkes-Barre, and they set up floors for events. And then, for graduations or concerts or what have you. So, they have hundreds of panels that they need to ship to a site, set up for a week, and then bring back. And before they could ship it to a new site, they need to wash all these panels. And it seems like a simple activity. Oh, they just got to wash the panels. Well, they got to pressure wash every single panel, and there's hundreds of panels. It could take them weeks to wash the panels. So that's a lot of labor. It's a very labor intensive, dirty job. So they came to us, and it was a great collaboration that I had some students that were interested to work on this project, and they got credit for it through independent study course. So they got a great experience, something unique to put on their resume. We were partially funded through Ben Franklin Institute. Mr. Ken Okrepke is on the left. He really helped with the funding of this project. And then just great project overall. So the company paid for some of it. Ben Franklin paid for some of it. And Wilkes students got a credits for it. So it was a win-win partnership. Here's 2 of our former graduates, Adam and Andrew. Adam's on the left, Andrew's on the right. And they're working at Toyota in Michigan. And Adam was one of my students that I worked with closely. He worked on another independent study course with me, and he presented at a conference. And I just remember for years, he always had it as his dream. He's like, I want to work for one of the big car companies, and I want to work for Toyota. And sure enough, he got himself an interview, and now he's working out in Toyota. So he's definitely happy with where he ended up, and it's all mostly due to his motivation. I will say that, but I like to think that And the experience he got at Wilkes as a Wilkes engineer really prepared him that he could stand up for applicants. You know, he was going up against applicants from the University of Michigan and University of Ohio, Ohio State, and he stood tall. You know, they said, "Wow, you have really great experience as an undergrad at Wilkes that we're not seeing at these other schools," and they hired him. So now I'm going to make it a little fun. I'm going to showcase some of the community outreach we do. We like to get involved and showcase science and engineering to local fifth graders and, seventh graders, ninth graders, all, pretty much middle school, early high school. Adventures in science, women empowered by science, webs. And it's a nice way we could give back to our community. Our students like to get involved and help the kids play with different engineering style toys and just kind of introduce what is engineering to students. One of the difficulties we have marketing engineering as a profession nationwide is a lot of people don't know what an engineer is and what it is as a career. You don't go to the engineer, you go to the dentist, you go to the doctor, right? You may have to call a plumber, but you don't really know what the engineer is. The engineer is the one behind the scenes designing all those cool things you use in your house. On the bottom left, it was a demonstration of a Rube Goldberg machine. It's kind of a fun engineering tool I like to use. I make it a design project for my advanced machine design class, and in this case, it was a great demonstration for kids. If you've never heard of a Rube Goldberg machine, pause the video, go to YouTube, and just look up Rube Goldberg machines. They're awesome. There's a really cool one I just saw recently. It was like a guy making a basketball shot. He was outdoors and he started this elaborate contraption, and then at the end it made a basketball. It was like a 2.5-minute video. It's basically a overly excessive and elaborate way to do a very simple task. But it's a great demonstration of energy transfer and various mechanical systems and electrical systems at work. This was part of my freshman class that I talked about. We had an egg drop competition where they had to utilize different materials and kind of a way to get freshmen involved in what is engineering design. Even though, hey, you may not have the math, you may not have all the tools that engineers who have graduated have, but you still can take different objects under constraints to purpose them for a specific task. And you have that ability even before college. I like to let my son try to design things as a middle schooler. Now he's a high schooler, actually. So here is the adjustable wheelchair. So now I'm gonna highlight several senior projects, but this one I talked about a little earlier, so I'm just going to briefly, here's what it looks like, and there's the contraption. And basically, once it adjusts to a specific width, it'll fold and then come right back to that width. So if someone has it adjusted to their liking, they could fold it, transport it in the trunk of a car, and then it folds right back. They don't have to worry about that. And that's kind of one of the features that makes our patent unique, and that was mainly our main claim. Because there are other similar type of adjustable wheelchairs on the market, but we're the only ones that go back to where it started from. So this was designed using CAD and then the physically built prototype, and it was a great collaboration. Heather, she's a licensed occupational therapist, and she came up with a lot of the core ideas, but then the students came up with the different gear mechanisms and screw mechanisms, and they actually built it, and I tried to input where I can as well, and we all kind of guided the project along. It was great. Another senior project, and I'm kind of, I've been involved in probably 100 senior projects since I've been, as a faculty member, so I can't highlight every single one, but I'm trying to just highlight the diverse nature of senior projects. The wheelchair was something, piece of equipment that was small, tangible, easy to grasp. This next project was students were advisor to, so I was an advisor to a senior projects team that was converting an old church into a parish center. So the team received a lot of real life experience working with the customer, and they were able to repurpose pews into creative furniture designs, and they actually got hands-on with the build. They modeled this all up. This is in a picture up here. This is a computer model showing all the different partitions that they were going to design to make this a functional parish center. They did acoustic analysis. If anyone's been in a church, you know that churches are designed to carry sound. Well, for something where you want partitioned rooms, you don't want it to carry sound. So they were able to do a lot of acoustic analysis on it. So electrical work, it was great project overall. And then we wanted to do some testing on the pew. So there's myself in the green, Eddie again, he seems to be in a lot of these videos, and 3 of our students. And we put strain gauges on the pew, and we just wanted to do some dynamic testing where if someone sat on it and started bouncing, would the wood break?
1, 2, 3, go.
So that was a lot of fun. We got to do some real world testing. And this is my absolute favorite part of senior projects is watching the students that most of them probably came in as scared freshmen, and I say, hey, you got to do a presentation today, and they say, what? I don't want to do that. But then watching them as they're seniors stand up there dressed nicely, confidently present, this is our product and this is how it works, and in Stark 101, which is the largest classroom we have at Wilkes, and it's just great watching them grow from young adults into adults. I'll put it that way, from freshmen to seniors. Here's a couple other senior projects I've been involved in. Pumpkin Chunkin', that was a great one on the left. High lift dump trailer on the right. So that was a way to dump maybe mulch into someone's yard with a fence, right? So a great practical real world problem. Our students are given a budget of $500 as a team, and they could. So it's a real world constraint. You have this much money to spend to design and build your product. Now the one on the right, it's going to cost several $1,000s. We knew that right off the bat. So they actually partnered with a local company that was willing to donate materials and labor to help them with all the massive welding, machining operations that were needed. And our students loved getting hands-on too. They spent days at the company helping them with, create the final product. But then the company would get the trailer at the end. So that was kind of the trade-off. So that was a fun project. There's the pressure redistribution system on the left, and that was my 5th patent that I previously talked about with Heather. And you could see all the electronics involved. And there's a load cell under the seat that basically sensors which section the person was sitting on, and would they, and to make it move. So there's like an air bladder with a pump. The one on the right is a liquid resin 3D printer. So that was a fun one. I had a group of students, motivated students, and a lot of these projects, they come to me and say, oh, I got this idea. So sometimes I have an idea that I'll pitch to the teams, or in the case, Heather was the one with the 2 wheelchair ideas. But then the one on the right, the student said, I want to build a 3D printer. I said, okay, that sounds like fun. I'll do the best I can to help you. So there's many different types of 3D printers. The one I showed you before was a fused deposition modeling FDM printer. This one's a liquid resin 3D printer, where it basically uses a UV light, which we have a projector there, that flashes an image into the resin and cures a layer at a time, and then it lifts up, and then it cures the next layer, and it continually flashes the image. So you can see how this one would go a lot faster than the previous one that would just draw a little line at a time. And they actually did get it to work, and I have some of their 3D printings that I usually pass around for a demo. This was another fun one, and this was a student-led one. They said, hey, when we go to a bar, the bartender needs to mix drinks by hand. What if we made an automated drink mixer? I said, that sounds like a cool idea. So they basically made up a system where they would program in different drinks with different amounts of liquid, and they would just push a button, and there would be a whole series of pumps that would mix a drink. So they could say Long Island iced tea, and it would go psh, 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 psh. and it would shoot it in. So for the final demonstration, what you're seeing there in Stark is not alcoholic. They're just colored food colors, but they wanted to demonstrate it in the building. And I said, no, you cannot bring alcohol in Stark. And then this next one was Rube Goldberg, which I talked about earlier. So this was a great project to be involved in. They got to design their own Rube Goldberg machine, a really large scale one. And they won the Online People's Choice Award in 2017. So that was fun. We wanted to go to the national competition, Rube Goldberg competition in Indiana, and we actually had it all set up, but then the Pi Day blizzard hit at 3/14/17, and we got pi feet of snow, at least at my house, and we cannot go. But they were able to record their video and send it in online, and then they got the most votes online, so that was fun. And here's another project that I want to showcase. It's called Unplugged, and they wanted to turn gravitational potential energy into electrical energy for the purpose of charging a cell phone. So that was a great project. You know, I was so happy to be involved in that one. It was basically, if you're out in the woods and you're stranded and your cell phone dies and you don't have an emergency charger, this is a way to create your own energy to at least juice up your phone enough to make an emergency call. I'm going to pause it here. So the very last senior project I want to highlight is Kraken Board Sports, and I was their advisor. They started out with their design in my machine design class. I have a design project in machine design. And they had this idea to make a winch so that it could be used to snowboard on flatland and wakeboard without a bow. So they started out in an undergraduate class, and then they actually built a prototype themselves over the summer because they just wanted to. And that's, a lot of engineering is just, hey, that looks cool, I'm going to try and make it. And then I was their senior projects advisor, where they refined their design. So that you can see on the right is their very first prototype, and the one on the left is one of their more advanced models. And then since then, they've started their own engineering design company in Wilkes-Barre. So, and they're actually selling these nationwide. So here's just a quick video of it in action. They're snowboarding with my son Eddie. I'll scroll just a few seconds. So you can see the winch spooling up, and basically they could design the gear ratio so that it's either provides high torque to wakeboard, or in the case of snowboarding, they could provide higher speed. But in this case, they weren't going too fast.
How's
that? Eddie, you like that?
It wasn't so bad.
Did you like that?
Except for the end part.
Yeah. So they, power is basically torque times rotational speed. So you can either get one or the other. So for wakeboarding, they want high torque to get up out of the water, and for snowboarding, they want high speed. And in this case, when they were taking Eddie, they just went at pretty low speed, but just kind of a cool video of it in action. And then here's the last video I have today, kind of showing this is one of my former students, Dan.
I studied engineering because I always wanted to be an inventor. I'd get to build stuff, take stuff apart, put them back together, hopefully make it better, maybe. Digital design and media art was something else I always loved doing. I always found that engineering and art and media art linked together so well because they both end up becoming part of the same thing after you work hard enough at it. And so I always wanted to study both. but it was going to be hard to do anywhere else. So I found here that there was the digital art minor and tried to pursue that. The most I've ever integrated all the fields together was when I started cracking board sports with my buddies in my engineering department. I designed the logo for the company, and I do media stuff, and I designed the website, but I also help design the product and be able to make sure the product is safe and do engineering so that it actually works at the end, and then find other people around the university, learn a little bit of business help. Really the combination of everything. The Wilkes Enterprise Center helped us out greatly starting our business. I never knew the amount of connections that were available in the Wilkes-Barre area. My favorite thing about Wilkes is that it's open enough that they let you do what you want to do. If you can find the path you want to take, you can find the help to be able to kind of form it and mold something unique out of it. I'm an electrical engineering, mechanical engineering, digital design and media art, computer engineering and physics student, avid razor scooterer, and I'm Dan Likens.
So that's such a great video. And Dan really is a great guy. You know, even after graduation, we still catch up time to time. Like, hey, you want to go to this local deli and tell me how's things going? And he really kind of does embody what Wilkes engineering is about. And I'll just go right into my conclusion here, that Wilkes will give you the skills necessary to be a successful engineer. College is different than high school for sure. There's way more freedom, but with freedom comes responsibility. And my advice to incoming freshmen is just seek help if you're falling behind. There are plenty of tutors, classmates, professor that want to see you succeed, want to help you, but we can't do it for you. You have to want to do it, and you want to have to work hard. And then, you know, usually I open up for questions. But again, I'll just say, if you have any questions, please feel free to email me, edward.bednarz@wilkes.edu. But here's one last quote I'll leave you with. And actually, Dan Likens is the one that showed me this quote from Steve Wozniak. And if you're not familiar, Steve Wozniak is the other Steve from Apple, you know, along with Steve Jobs. He's Woz is basically the engineer that worked and worked and worked to make it work. And I'll just read it to you. I hope you'll be as lucky as I am. The world needs inventors, great ones. You can be one. If you love what you do and are willing to do what it takes, it's within your reach. And it'll be worth every minute you spend alone at night thinking and thinking about what it is you want to design or build. It'll be worth it, I promise. And you know, just as the last summary for engineering, it's definitely a challenging field. You know, a lot of math. There's several calculus classes to get through, so you have to have some aptitude to math. But above all that, I think you have to work hard at it. And then it's challenging. Not everyone does it. You know, some students enroll, drop out, to be honest. But the ones that really have that dream that say, I want to be an engineer and I'm going to work hard at it and I'm going to get through these tougher courses, because there are fun classes too. You know, even though you're like, oh yeah, I just spent 10 hours working on this project, it felt enjoyable to me the whole time. And I loved the end result from it. So, you know, hopefully this is a career that you're passionate about and you want to pursue. And I will do everything in my power to help you get there and help you succeed. So thank you for watching this video, and take care, everybody.